you told me you have to.
You can see the screen.
Yeah, we can. Yeah.
Then I'm ready.
Yeah, I think we can start. I think we got enough people. Normally we get like a 30, 40. Let me see. Yeah, we have good number of the people. So let's start. Let me see. Yeah, I think we have enough. So good morning, everyone. Thank you all for joining today's M&I seminar. It is my great pleasure and honor to introduce today's speaker, Dr. Matthias von Herrath from the LaJolla Institute of Immunology. Dr. von Herrath is one of the well-known and well-recognized, I would say well-reputed scientists in the field of type 1 diabetes and autoimmunity. I've been following his the work for a very long time. And also I happened to serve on a couple of study sessions where he was on. So that's how I know him. And but I am an admirer of his work. Currently, Dr. von Herrath is a professor at the LaJolla Institute and an adjunct professor at UC San Diego. In addition, he has been serving as a vice president and a senior medical officer for Novo Nordisk Pharmaceuticals for the last 10 years. Dr. von Herrath received an MD degree and completed a PhD equivalent thesis from Freiburg Medical Institute in Germany. And I believe it is in 1988. And he served as a clinical fellow for a couple of years in Germany before moving to Scripps Research Institute at LaJolla as a postdoctoral fellow in 1991. He continued at Scripps Research Institute at assistant and associate professor levels until 2001. And I believe he joined LaJolla Institute as an associate professor and became a full professor in 2008. And he has been there since then. So he has been in LaJolla for a long time. So Dr. von Herrath's research focus during the last few decades and has been on immunology of type 1 diabetes and the clinical, translational, and immunotherapeutic aspects of this particular disease. His lab has published more than 120 original research papers on these areas, and also several dozen additional the papers from collaborations. I noticed that he has collaborated with many of the major type 1 diabetes research groups around. And I noticed that recently his publications have been increasingly been on human type 1 diabetes rather than using preclinical models. Now, Dr. von Herrath also published about 100 review articles on type 1 diabetes and autoimmunity. All of them were very informative. They were very useful me, at least, when I started type 1 diabetes research in my lab several years ago. Dr. von Herrath serves on the editorial boards of several high-profile journals at various capacities. These journals include JCI, JXMed, Nature Immunology, Journal of Immunology, and that list really goes on. And he has received awards and recognitions from the national and international organizations like JDRF, ADA, NPOD, and etc. for his research contributions to the type 1 diabetes field. And I believe he served on multiple NIH study sections. I think he's still a regular member of HAI study section. He's well funded with multiple large R01s and other grants. And his achievements are pretty, it's a very long list. I can go on, but in the interest of time, I would just stop here and without any delay, let's hear from Dr. Matthias von Herrath about how pancreatic beta cells orchestrate their own demise in type 1 diabetes and the emerging therapeutic concepts.
Well, thank you very much for that nice introduction. I'm very happy to be here. Please interrupt me anytime if there's a problem, notably with sound or video. Then we have to go to a backup plan. And also, if you have questions, I will stay within the hour. And you shouldn't be shy to interrupt me because we can always adjust the number of slides in the talk. I want to introduce today to you not necessarily a novel concept, but a concept that's maybe underrated so far, and has to do with how organ-specific autoimmunity is controlled. And that will be the first part of my talk. Then I want to give you some insight in some translational avenues that we have been following. My work is divided in the sense that I do some basic research in LaJolla Institute. And then for the translation, this all occurs at Novo Nordisk because of trial design, financial issues, and so forth. So we have divvied things up like that. I will show you some published trial data from Novo Nordisk. And as a disclaimer, I will refrain from propagating any off-label drug use or otherwise advertising drugs from Novo Nordisk. And for this talk, it's pretty easy that because we are talking, especially when it concerns the GLP-1s, probably about drug class effects. So these are general considerations. Some of them are clearly preclinical and basic science. And all of this has nothing to do with the drug approval at this point. So I think we should stay pretty balanced. So when you look at type 1 diabetes, all the way from the old days when I got into it, which was in 1991, till today, I think we had to undergo the sobering realizations that while we can unravel the genetic and environmental causes for the disease, it's also unfortunately very multifactorial. That makes it difficult to derive from this insight, genes, environment, anything that we can directly target with the confidence that I would completely abrogate the disease. That's why things have taken so long for type 1 diabetes. I think we also, and that ties into the main theme of my talk today, have to realize that there are probably factors that we don't fully understand yet about the pathogenesis of the disease. And that could be the nervous system, local things in the pancreas that deal with the beta cell and so forth. And really what argues for that is that when you look at immune interventions, the ones that have been able to preserve beta cells, some listed below, especially the non-myeloablative bone marrow transplants that Walter Velli conducted in Brazil should make us pause, not only because it's pretty drastic intervention, and because of that, in my opinion, very unlikely to reach mainstream because of the side effects. It's like really an immuno-oncologic conditioning for children that's usually used for cancers. It's too drastic for type 1. But what should make us pause is that even with that, while there was some disease-free individuals, maybe about 30%, still the disease came back. So there is something about this organ-specific immune diseases that make him come back. Maybe it's simplistic. It's just in quotes memory cells that are already sitting in the organ. But maybe there's also other factors that make these memory cells reignite and become aggressive. So that's my my current view on the matter. As already mentioned during the nice introduction, we shifted more and more in our understanding of disease from mice to human pathology. That doesn't mean that we actually haven't used mice quite heavily as a leg to stand on to prioritize interventions, also at Novo Nordisk. So you shouldn't misunderstand me. I by no means think that mice are not useful. I think they retain their place in sorting certain important factors, especially what you cannot sort in pathology, where you only have a one-time snapshot of what might be happening in humans, and you lose the whole dynamic issues of the process. What we have learned is interesting, and it goes a little bit that this decline of beta cell function in type 1 is probably not linear. That also goes along well with the trial net data. And in the pre-diabetic phase is probably even, in addition to that, relapsing, remitting. Why do I say that? Because there's times where we get pancreata from autoantibody positive organ donors, and there's no infiltration in there. But these individuals already obviously had autoimmunity as evidenced by antibodies. And they have a higher risk to develop type 1 diabetes, which you all know about with the antibody occurrence. So it's probably such that the organ, almost like in a climate change, is stabilizing a state that is important for our body, in this case, like insulin. And then when that doesn't succeed, it cataclysmically goes into a different state. This cataclysm, how these feedback loop type of statuses in the immune system get stabilized and can break down, is a bit worrisome, at least if you follow that analogy with the climate change, because it means things will be stable for a while, then they start making noise. You know, at the moment, we see a fair amount of noise, maybe, we don't know. But when that noise becomes too much, then the status changes. It's sort of like a reversal of an Atlantic current or something like that. So it's not particularly encouraging. Then the system equilibrates, unfortunately, at a state that is, again, reasonably stable, but not enough insulin for the body. Prevention or treatment-wise is actually not bad, because in this stage, for sure, in stage 2 or earlier, there's enough beta cells to have a big effect. And the folks from prevention with anti-CD3 have demonstrated that you can prevent diabetes 2 to 3 years. And even after onset, you can, what we think, still preserve a meaningful amount of beta cell function. So these are the key learnings. We will talk about what I show here, the class 1 upregulation, in a few minutes. Now, this is sort of the pathogenetic thrust of my talk, where we need to rethink things. But it's really not, as I said in the beginning, it's not like a revolution or anything. It's just that we have to keep in mind, in my opinion, that for the control of autoimmunity, there's several checkpoints, and that organ-specific checkpoint for organ-specific autoimmune diseases is probably quite important. You have, of course, long-time described thymic tolerance, but we know that there are cells in the periphery. The most fun review on that is by Mario Ehlers. It's called, I just found it yesterday because we are writing on a piece. It's called "Who Let the Dogs Out?" This pretty fun review to read, because it's talking about how these autoreactive cells are arriving in the periphery and what on earth they're doing. And then notably, many people, certainly the Bluestone lab and so forth, have worked on peripheral immune regulation, but we know also from the Caladius trial that the polyclonal Treg therapy, while it might be very useful for stronger inflammation like transplantation, GVHD, in these organ-specific diseases is difficult to realize. Probably have to make CAR Tregs, antigen-specific Tregs, which many, of course, are working on. But so this systemic dysregulation is maybe not the main cause of the normal type 1 case, also because the clinical presentation of your average case is not that you have multi-organ inflammation and dysregulation. So it's not like a FOXP3 deficiency. Now, that doesn't mean that there are some cases for sure that are dysregulated, especially if you start seeing patients with many, rather than type 1, other autoimmune diseases at the same time. So you can imagine that that pushes more in a systemic range. If they have celiac, if they have thyroiditis, you're going to go like, well, wait a minute, in this individual, there seem to be many things not properly regulated. And so probably a clinical spectrum. What I'm getting at is that for a case where there's only type 1 diabetes, you probably have a loss of organ-specific control. And we have now a fair amount of evidence, and this is what we will go through, not only that in healthy individuals, there are some autoreactive cells there, okay, in all of us, but they usually don't do anything. Maybe there are regulators, we don't know, but that the beta cells themselves can stick out like a beacon and become visible to the immune system. And we will discuss MHC and other factors that probably play a role. And we call it unveiling from a camouflage stage. And we think that that's actually quite important in the body. In the CNS, probably similar, because the body doesn't want neuronal cells, and here for beta cells, neuroendocrine precursor-derived cells, to be really highly immune visible. Similar in the hair follicle for alopecia, similar in some other organ-specific autoimmune diseases. And if you think about it, the pathology of type 1 is patchy, like vitiligo or alopecia. George Eisenbart always used to say that. And some organ-specific diseases like arthritis are even symmetric. Actually, often also vitiligo is symmetric. You think about this. How would this be if there's a systemic dysregulation that you have a symmetric presentation of a disease in joint, only in these joints, let's say? Why not here? Why not here? Why not other joints? And that is calling for these other factors, which could be neuronal, that have to do with the unveiling of the target organ. Again, this argument, this is not an argument to say this thymic tolerance is not important. We all agree on that. There has been 50 years of research on these things. This is not an argument to saying, oh, peripheral immune regulation is not important. Obviously it is. We know what happens when it falls away. These are not the argument. We just have to look at that this balance is where defects lie. It might vary between patients depending on their clinical manifestation, and this local situation might be important. If that's the case, actually encouraging for therapies, because it means anything that can recamouflage the beta cell might be quite useful. And we will talk about this later on. These are all these events that we can list. We have worked on that quite intensively. The class 1 is, of course, an old story from Fowles from the 80s, and it fell out of fashion. We looked at this quite systematically recently, and we can find that the class 1 is up before there's infiltrating T cells in many islets. So it seems to be a primary event, which could be caused by many things. We will discuss it. We also find class 2. I think we can put that situation, this controversy to rest. The class 2 comes up later. Would be nice if it would be a first event in prediabetes, because you have autoantibodies and you could argue about early recognition, but clearly it's patchy and it comes later, at least in our studies. Many people have described this pro-insulin-insulin ratio shift, sort of like a constipation of the beta cell, that it doesn't work maybe as well as it should. We had a paper on IDO that's lost by beta cells. We don't know what it means. It was a descriptive paper. You can make all kinds of hypotheses about this. Obviously, a tolerogenic enzyme, Andrew Meller, Ursula Grohmann have worked on this, but is it important? We don't know. IL-17 is upregulated by beta cells in type 1, as well as type 2. Interesting. Certainly, if you look at Peakman's data, not a good cytokine to have there. Why the beta cells make this, we don't understand. What it contributes to disease pathogenesis, you can make many hypotheses. Obviously, once it would get into activating certain T helper cells is not a good thing. It fits with our anti-IL-21 trial in certain forms. And then there's people who have worked on beta cell death, whether it's good or bad. It links into the danger hypothesis that Pauline Matzinger put forth. And we can now, by these groups, in many cases, put very interesting molecular correlates on that. We had a collaboration with Nick Webster at UCSD, where we can make beta cell dysfunction or sometimes die. And we thought initially it's just in quotes, a splicing enzyme. We thought that this is just a model that the beta cells die. But actually, immune system becomes interested in them and then finish them off. So this issue that something is wrong with the beta cell, then the immune system goes like, whoa, there seems to be something that I should maybe be interested in. And then notably CD8 cells finish this off is maybe a good hypothesis. Doesn't make it so much easier for therapies, because CD8 cells in solid organs is a beast to deal with immune therapeutically because of the safety, as you can probably also relate to with COVID and flu and other diseases. All these diseases leave memory cells in the target organs. So if we wipe them out, it's not a particularly good move in terms of immune safety. A few words about the MHC class 1, how it presents itself, and how pronounced it can be. Here, even in an insulin-containing islet, 1 year post-diagnosis, if you look at this, there's still insulin, and the whole islet lights up. So that also shows you it's not only the beta cells, there's a lot of class 1 on alpha cells. We think that alpha cells just don't get targeted as much because 2 reasons: they don't die as fast as beta cells, for reasons we don't understand, and probably the epitopes presented by alpha cells are not as immune recognizable. Insulin is certainly, in our opinion, a key antigen, not the only one. And here you see the infiltration or immune interest is actually pretty mild. This one was one of our best islets. and the number of CD8s, as you can see, is not like a swarm like in the NOD mouse. It's mild, and you have even less CD4 cells and less B cells and less macrophages. So it's a mild insulitis, reminiscent of alopecia. That looks pretty similar. MS looks pretty similar. These are not profound immune inflammatory diseases, but there's other changes like this MHC, which is actually pretty profound. When you look in the pre-diabetic phase on islets, this was Mehdi's paper published recently, you can see that this MHC, as I indicated, starts in the pre-diabetic state. Then in insulin-containing islets is higher. Once the insulin is lost, this all recedes. So there is something that precedes immune infiltration, but there's also then at the end, when you go back, some correlate between immune infiltration and pathology and the MHC that is reasonable. So it goes together. Once the insulin is lost, as we think, as an antigen and maybe other beta cell proteins, the whole process goes to sleep. You can see this in the human pancreas. Those lobes that are already devoid of beta cells, immune system is not interested anymore. Just the whole disease process goes to sleep after this has been done. So that's for the MHC. You can have a long argument why that might be. I put all our hypotheses here. None of it is proven. Means lots of more work needs to be done altogether. And there's plenty of space for many people to do a bunch of good research there. Probably, optimistically speaking, hopefully in the next few decades, hopefully not beyond my lifetime, we will see. I hope we can crack this nut at some point. Yes, why do I say this? There is some promise in avenues. There has been active research on viruses by many people, most notably to the NPOD consortium. The picture that's emerging, when we look at this, we looked at herpes virus 6, LaJolla virus more recently. Other people like Teresa and Maria Craig and folks in Oslo looked at enteroviruses. There's more viruses in these pancreata of type 1 diabetes, but you cannot correlate any of the viral presence by protein staining to the pathology in a given islet. So in a way, it hangs together with the disease, but it doesn't hang together on a per islet basis with the pathology. So that gives us a little bit of a conundrum, because if I look back at my good old times in Michael Oldstone's lab, he would always say, Matthias, there's course postulates. You need to learn these course postulates. Which kind of means if you have a virus there, you also have to have the T cells to the virus coming where the virus is. And these are not fulfilled, but the virus is there with the disease. So maybe the pancreata that are already smaller, I threw this on one of my first slides, Atkinson described this, they're also more sensitive to viruses. There's recent movements by Francesco Dotta and Decio Isaac and Teresa who look at viral response genes that might be altered. So maybe you're looking in addition to the thymic selection and peripheral control at a target organ that has a wrong viral response, and because of that is more susceptible. And that might occur in different ways, maybe even in coronavirus in a tragic way, that those poor people who develop this severe COVID have somehow a lung response that is not appropriate to deal with this virus in a proper fashion. And then this somehow persists longer and wreaks more havoc in the organ. So that's how the viral story is. I think our friends in Oslo with an antiviral trial will help us to sort whether the virus infections and how often they are pathogenetically important. We had papers on the innervation. We could switch off in this one observation in the mice completely autoimmunity in the LCMV model. And that's a pretty strong model just by cutting innervation or by medicinal intervention to alpha receptors. That was interesting. It really opens up that alopecia, vitiligo, arthritis, maybe that there's something about the symmetry that is nerve system directed. And it argues, again, interventionally, some companies are doing this, trying to do this, that we should try to selectively become able to interfere with innervation. That's not an easy task. You can, of course, not give systemic nerve killers or nerve modulators to people with type 1. You can also not just walk around and start cutting nerves in the intestine and hope for the best. That has to become more selective. We talked a bit about cytokines. That certainly is interesting. We looked intensively what cytokines are made by beta cells. IL-6 constitutively, we have no idea why that is. IL-17 is upregulated. Others are not, TNF not, in the beta cells, I mean. In interleukin-1 is not in the beta cells. They're probably made by other cells. The hypothesis is easy. When the class 1 goes up, you have CD8 cells there, they should kill the islets more. And we talk about this for the next few minutes, and then I'm done with my pathology part, and we can also take some questions. So we used to do this tetramer stain just for pre-proinsulin specific T cells. The one epitope A2 restricted that Mark Peakman described as a natural process peptide epitope long time ago. And he had a clone to that, and you can make, because of that, good controls for the tetramers, because you can control your tetramers before you do any stains with clones. So now the way we do it, we find the islets in this pancreatide with insulin glucagon stain, like shown such. We measure precisely where they are. We put a mask, we have this slide scanner. Then we strip the sections, use the same sections, and then we stain for tetramers. And we can then quantitate whether these cells, CD8 cells, proinsulin specific, A2, whether they're in the islets, around the islets, in proximity, or in the exocrine pancreas. So that's what we did. We just wanted to get a whole picture quantitatively, who is where and what these guys are doing, and then draw a pseudo timeline from healthy over pre-diabetic to type 1 with insulin islets to non-insulin containing islets. And that's as good as it gets with the pathology. You have to draw these pseudo timelines. They're obviously from different individuals, and you have a fair amount of variation. That you can see here. What is the outcome of this? Showing here the general CD8 cells, pro-insulin CD8 cells, and the relative frequency. The relative frequency, to take this in the beginning, stays about the same of pro-insulin CD8s among CD8s. What is really interesting is two things. One is already in the exocrine, they're increasing. In the islet neighborhood, they're increasing. Next slide, I will show you the increase in the islets. But they're also there in some of the healthy controls. So we think there's this issue that you have autoreactive cells leaking, and they are physiologically there in all of us in low numbers. And you also find this in the blood because of that Mario Ehler's paper and some others who have looked at this. But then in type 1 diabetes, there seems to be an increase in frequency and an attraction, an increase in overall numbers, I should say, not the relative frequency, an overall number, and an attraction to the islets. The islets, mostly the insulin-containing islets, which makes sense. We're measuring reactivity to an insulin epitope, and when they become deficient, this whole thing subsides, as we have seen many times. You can ask, how many other epitopes are there? And other people like Roberto Malone and Maki Nakayama have worked on this. Insulin reactivity is prominent. It's not the only thing. We think, based on George Eisenbarth's old data, it can be causative, but that was in NOD mice. There's also interesting data in the NOD by Tom Kay that shows, together with Eisenbarth's data, that insulin is essential for initiating disease, and this IGRP reactivity just goes on top, but doesn't contribute to the disease. So we believe insulin is a good primary target also because there's so much of it there. We had an interesting observation in the NOD mouse. We looked at insulin reactivity versus an LCMV neoantigen that was published a long time ago. And when you put a completely non-tolerant thymic, non-tolerant LCMV neoantigen in NOD islets and look at the normal disease course, the acceleration is minimal over, I think we looked at 30, 40 mice. So that means that neoantigens, yes, can play a role, but maybe only a minor one. And so we see this maybe also when Bart Rube and others looked at post-translationally modified antigens. We have reactivity, but it seems to be minor in frequency. Now, does this mean it doesn't matter? We can't be so rash to say this, because if you had lots of minor antigens that get added to the process, all of a sudden of these small 2 to 5% effects, you can easily say, well, then you have 10 minor antigens. All of a sudden, you're 50% faster if this type of thing happens. So I think the jury is still out. I think we conclude from this that insulin reactivity is pretty high in frequency, and that there is a local control of whether the beta cells become visible to these cells or not. And therapeutically, that means to us that you could not only systemically immune modulate, which by nature will always have some side effects, but also target the beta cells themselves. And we talk about this in the rest of my talk, just giving you some glimpses of what we have done, mostly with Novo Nordisk. But at this point, we can take like a short break just to divvy it up as long as it's fresh in terms of whether you have any questions about the pathology that you would ask now, because we're now shifting gear to clinical trials and these type of things.
So really interesting. On the intra-islet CD8, they have a certain type of chemokine.
So we didn't look at this carefully, and we could not ascertain with our staining whether they do. But the Bar group and others have looked at this and should get credit. Sally Kent has looked at this. They have isolated them. Certainly they make IP10. People in general agree on that. And probably some other cytokines that would be more feeding in the interferon pathways, which would not be good. And then also Mark Piekman argued for a role of IL-17. And it would probably be interesting to see, also because we see that the beta cells upregulate IL-17, what an anti-IL-17 could do in type 1 diabetes. And I think there's trials underway. I just don't know how big they are. Novartis is the company who had an anti-IL-17 because they use this, as far as I'm informed, in psoriasis, where it's very successful. So one has to see. Blocking the interferon pathways is difficult. We would have to get there in a more circumspect way, because you cannot, especially not during COVID times and with the genetic evidence that was published, can probably not run around and block interferon pathways, especially not in young children. That would probably be really bad, especially as COVID is probably going to be around for a while. You're going to get very rapidly with an infectious disease like this. I would predict if you block interferon pathways, you're going to get a signal of children in particular, but then also others getting really ill when the interferon pathways don't work, right? So we are still sitting with the disease between a rock and a hard spot with the immune modulation, right? Because of memory cells in a solid organ, they usually have to be there for viruses, so not good to eliminate them. That's also a reason to do something locally. Interferon pathways, well, great, but who wants to block interferons systemically these days for a disease like type 1, where you have insulin and pumps and CGMs, where at least you can preserve life with these interventions? You see what I mean? So it's a tough situation, but good question. Very good question. And probably there's some TNF. You know about the trial from J&J, and that was pretty good success. Blocking TNF with the golizumab that they had in New England Journal. And yeah, and that was the second anti-TNF trial. So I think we have a pretty solid story also for DNF. So we can say TNF, interferons, IP10, IL-17, that's sort of the players. IL-1, no. The trials were negative, and we cannot ascertain any higher expression across the board in type 1 and type 2 diabetes. Is too heterogeneous. So inflammasome, not so much. IL-6, we don't know. There has been trials about this. And it's a very dual function cytokine. Some people say it goes up during exercise and it reduces insulin resistance, so it's good for you. But then other things, it's probably not so good for you. So it's a difficult target. As a disclaimer, Novo Nordisk has in-licensed an anti-IL-6, that's in the public domain, but for prevention of inflammation in cardiovascular disease. And you can read more about the just finished Zeus trial about this. So it is very interesting molecule, and how much it does in the beta cells, we don't know. But if you have Amelia Linnemann talking at some point, she probably can tell you much more about IL-6 than I can tell you. She has some very interesting work on that. So that's what we know a bit about cytokines. I find cytokines fascinating because what I wouldn't have predicted 20 years ago, that these guys have all different function in different diseases. Like you block IL-17 and psoriasis, then you block TNF and arthritis, and you get a whole other slew of specificities there.
Let me ask you, Sophie, you have one, I think you have one more question.
Go first, and I have one more.
Yeah, so let me ask you this: IL-17 expressed on beta cells. So they're like basically the cytokine promoting the recruitment of immune cells to the islet, leading to the destruction. Because in general, IL-17, especially along with IL-10, is protective in type 1 diabetes, especially in the mouse studies, and the people have shown in mouse studies. Right? So, what is IL-17 doing in the beta cells?
Well, I think, and be coming to that when I talk about organoids, we are missing dynamic understanding of the human scenario. And I think we can do something with organoids about it. We just don't know. We really don't know. In the wildest days, when I had a conversation with Kevin Herrath the other day, I mean, if we really want to be humble in humans, we can make all these hypotheses that are put out there. But for sure, we do not know whether these CD8 cells in the islets would be regulatory cells. You know, I mean, if you really take what we know at face value, we have to be really humble. And we cannot say, oh, here's some IL-17 for sure, it's bad. It's a good question you ask. I mean, that's precisely the questions we should be asking. And I'm a big friend, that's why I like these questions you're asking, of always taking a step back and saying, like, wait a minute, we think we know this, but maybe we should have another look, and it's the other way around in this scenario. I think, and some of this, I think we can address in organoids. I show you some data about this, but we'll have to see. Because of course, with the pathology, we miss all, we can do proximity analysis and these type of stuff and pseudo timelines, but we miss the dynamic process and the set points of things, right?
Yeah. So in type 1 diabetes, the manifestations, in some cases, in salivary gland and other organs, is it in humans? Is it because of some sort of antigen cross-reactivity, or just a pro-inflammatory response? It just makes those organs susceptible.
I would think that those patients who have more other organ manifestations, that those are the patients who have who start pushing into this area of systemic immune dysregulation. That's why I put in the beginning that I don't want to make a statement that Tregs wouldn't be important. I think that would be outrageous. We cannot just say this. I think it will grade between patients. I personally think we are far away from individualizing any medicine because we don't have any drugs in this space. But in the long run, the way this picture is being painted, like for other diseases, that's where probably you can be more individualized. You take a patient with many, maybe severe autoimmune manifestations, and you will be more inclined to prescribe something that is a systemic modulator. You take a patient who has only a local problem, and you will try to do something local. Well, as a point-taking extreme point, I sometimes get very small alopecia lesions. So obviously, I'm not taking an immune suppressant for that. I'd rather shave my head, although I grew a ponytail over the quarantine, but I'd rather shave my head. But the way it's treatable, you go to a dermatologist and you put a high dose cortisone in the lesion, and it's a done deal. You can just treat it locally, right? Because that's the only autoimmune manifestation. If I had, in addition to this, A, B, C, D, E, F, systemic manifestations of other diseases, would treat probably or consider treating with an immune modulator, because I would go like, whoa, I have IBD, I have diabetes, I am developing all these problems. Maybe I should suppress things a bit, right? That's where I think that goes in my mind.
Go ahead, Sophie.
So you partly answered already, but so I was wondering, when you did the staining in islet, did you look at other immune cells, and particularly the balance of the Tregs and the CD8, especially pre-diabetic, right?
Yeah, so that's a very good question. Not me, but many others in NPOD did this, so they deserve credit for that. The group in Exeter and Teresa Rodriguez and folks in Gainesville. What is emergent is that the CD8 cells are the most frequent cells. Tregs directly in the islets, almost none. Again, that doesn't mean they don't play a role, obviously can do this in the lymph node, right, as they might also do in mice. But probably locally in the islet, not so much. There is certain cases, the only one that are in different set points is B cells. And what has emerged is that in younger patients, there's more B cells. Piekman and the Exeter group, they published this. That might be the only true, what you would want to call endotype. Although I'm not even sure it's an endotype. I think it's just a graded thing. Young kids who destroy their islets fast, they just get much more immune participation. For the same reason, they might deal with the COVID much faster and eliminate the damn thing before it makes big havoc. They might have a higher reactivity to islets if they're unlucky. So that's how the grading is, right? So we cannot conclude from that Tregs don't play a role. We can probably say in the islets, in the physiological disease process, they probably don't play a big role, but that doesn't mean that you couldn't send a CAR Treg there, right? So it doesn't, in my mind, therapeutically, we are not limited to what happens in the natural disease. It might be this happening in the natural disease, but you come around the other way and say, well, now I tackle this therapeutically in a different pathways. And of course, there are many examples for that, to go about it this way. Right. Let me tell you a little bit therapeutic things so we don't run out of time. I'm going to skip some slides just to get an impression what's happening. So we ran based on this duality, a combination therapy. And the rationale was to do something that's more maintenance and local for the beta cells, the GLP-1 agonist, okay? And it's probably a class effect. So this is a novel drug, but it is a class effect, and that's the two we used, and systemically anti-interleukin 21. Some of it was opportunistic. Anti-IL-21 had been an arthritis, and we needed two drugs that regulatory-wise we could put together in adults with type 1. And it was a large trial, the largest trial to date done in adult type 1 diabetes. The IL-21 had good evidence in mouse models. It's a multifactorial cytokine. It had been used in knockout mice. Evidence was good it could play a role. The GLP-1s, in addition to enhancing glucose-induced insulin secretion and being used in type 2, obviously, they can decrease beta cell apoptosis and interfere with stress. That was for us a big reason to use them. There was this one paper from Luther and Chantal that looked at this, and that was published before. So we thought we had a pretty interesting case there. We added to that, and I wanted to show you this just as a platform. We did these spheroid organoids with a company in Zurich, Switzerland. And the way the model goes is we reassemble human islets, same size, put them in plates. So it becomes very normative and reproducible because all the islets look the same, not like a normal islet isolate. And we do build an immune attack model, first with cytokines, then but just with alloreactive lymphocytes, then spiking in autoreactive clone. And we asked, you can read out with glucose-induced insulin secretion. They hold themselves pretty well for 2 weeks, these islet organoids. And we can ask whether there are drugs when you throw them in the mix that help to maintain this glucose-induced insulin secretion. And the GLP-1s here, as shown here, were one of these that at least in some donors, there's variation with the GLP-1 receptor between islet donors, had this function. So that was the last leg to stand on. We also think, in terms of the many questions you asked about the pathology, that these at least 2-week dynamic human islet attack models that are better than our old 51 chromium release assays from the 90s can be used to sort certain things. You could say, well, how much IL-17 might be there? You can say, if I subtract out NK cells, does it still work? You can say, if I add an aggressive clone that makes interferon gamma, how much does this contribute to this situation? So you can ask some dynamic questions. They're limited. If you want to ask questions about trafficking and egress, obviously learn nothing. It's not built for this model. If you want to ask about innervation, well, good luck. And no nerves in there. So some things that you will not see, but other things I think you can address. I will just want to show you, this is our attack model. So it's an overkill. We literally eat up those islets with activated lymphocytes. So anything that works in there is pretty good. That's not what you see here on the right-hand side. That's not how probably human diabetes works. You don't have like 5 kilotons of reactive lymphocytes coming to the islet. So it's an overkill model, but that's not bad because it's like the NOD mouse in recent onset or LCMV model in recent onset. If you set the bar high, you can say maybe you have a higher chance of this working in humans, which has been notoriously difficult. So that's the trial data. This was published Lancet Endocrinology. You see, we are pretty happy with this combination therapy that we can maintain glucose-induced insulin secretion and C-peptide over time. When we withdraw the drug, we lose the effect, just like with many other therapies. So it's not an immune reset. The combo works better than the GLP-1s or IL-21 alone. Compared to others, not a fair comparison here, ages were younger. This is adults, so this might actually work better in younger people as a indication. But we are on par with other intervention, anti-CD2, the ATG, abatacept. So it was a good trial. It was a good combination therapy and very low side effects because of the nature of these molecules we're using. So I think the therapeutic field should consider that this is a valid avenue. There's much work needed. We need to, it's by no means a slam dunk to just put GLP-1s in type 1 diabetes. It's a different disease than type 2 diabetes. There's many precautionary trials that need to be run, and they're ongoing right now, not only by Novo Nordisk, but by other groups, some academic groups, that needs to be sorted. So it is not there yet. One can consider, and this is where it gets really interesting, this is a subgroup analysis, post hoc, okay? So we reach primary endpoints, I should have said, C-peptide, reduction of insulin dose, good trends in HbA1c and reduction of hypos with this trial. And we had 310 patients, so we could do a subgroup analysis between those coming with high versus low C-peptides. A bit easier in adults because you get about half of them with high C-peptide. In a high C-peptide group, the maintenance of insulin, of C-peptide, is as good with a combo in red as with a GLP-1 alone. So you could argue that before you have more immune destruction to get from here to here, which we would argue is happening, because you lose C-peptide, you already have this cataclysmic event reducing beta cell function. Before that happens, maybe the GLP-1s alone are as good as any immune modulator in preserving beta cell function. That would be encouraging. What is not encouraging, always under treatment, already have this parallel decline. If you stop treatment, it gets even worse. We have one of the few trials where we actually have these washout periods that were part of the trial. So it comes back to my first argument. We haven't solved the problem, right? This here is like as if you take a statin, and while you take the statin, your cholesterol keeps on going up, nevertheless, something that all of us who might take statins not hoping for. So it's not optimal. It's also not optimal if you take an antihypertensive, and there you take the drug and you think you're okay, but your blood pressure keeps on climbing. Also not good. So we are missing something, you know, that mechanistically is not related to these two entities. Sobering. Maybe the innovation, maybe the virus, we don't know. So that's what we have. That's what we have to build on. Some of it can also be built into islet transplantation. So that's where we are. Where will we go in the future? We will try to do more with these spheroids on organoids. In addition to the pathology, we would like to use the system to subtractively get a relative dynamic idea what other players do. You already asked about B cells and NK cells. Some of it we just don't know. Doesn't mean if there's less there, they don't do anything. That would be premature to conclude, right? And then this disease recurrence, despite immune therapy bothering us, we have some observations from old days that Uke and Hubert Kolb and Johnny Ludwigsen already had. There's something in the serum, Olaf Berggren also worked on this, that impairs islet function. So you take serum from diabetics and you put it on healthy islets and impairs function. It's not cytokines or high glucose. Very curious. And is it reproducible? We don't know. Is it a strong effect? We don't know. So it's sort of we wrote an R21 about it because it's early things. And I think we want to study this in addition to the spheroids, also in live pancreatic slices, again, to get at more the dynamics of the human process. So that's what we would like to do in the future. And that's the end of my talk. We have 5 minutes, so that's not bad. We can have a little bit more discussion. We worked with the Insphero company in Switzerland who developed this spheroid platform. We can now also do in LaJolla. Novo Nordisk is only a few key people who helped us in the Seattle unit, but it was a large trial, so you probably go in hundreds of people who participated. You can find it on the paper. And then I showed you data from Christina, Stefania, and Mehdi, and Sakti from La Jolla Institute. And that's that. And thank you for your time. And of course, if there's more questions, you can also email me after the talk. It's always a bit weird, these Zoom visits, because you're only there for an hour, but you know.
I have a very quick question. Sorry, I saw, so if you put serum from diabetic patients, it impairs the beta cell function. What if you put serum from pregnant women? Would it improve beta cell function, not change?
That is a great question. And Michael German and UCSF, he would like that question because he's been working on this factor. I think that there must be something there. Andy Stewart also has worked on this islet expansion and published on these DYRK1A inhibitors, right? There must be something there that could also improve beta cell function. And that avenue that you could outpace beta cell destruction by enhancing their reproduction, that's therapeutically probably important, not in a 2-year-old child, but in a slower onset diabetes that manifests itself at 20 years of age or later. You would have a pretty good window to do something about it. It's a very good question. And whether Olaf Berggren had a paper that saying that the factor is APO3E, we don't know. Maybe it's a lipoprotein, but then that would also have to be the case in many type 2 patients, most notably. But the type 2 patients, many of them have dyslipidemias. They don't just lose their beta cells in 5 seconds like type 1. So we don't understand the difference between that, right? But very good question. This expansion in pregnancy, I find remarkable. It makes you think if we would understand the factor in mice, I think is better sorted. But if we would understand it in humans, we could do a lot about the disease, right?
Yeah.
Are there any questions? No. Okay, let me ask you this. And so GLP-1, and there's a lot of controversy over GLP-1's effect in terms of whether it is inducing insulin production or inducing some sort of islet on the beta cell regeneration. So what do you think the real effect of GLP-1?
I think from the mice, we overestimate a beta cell regeneration. And they might do it in very young humans, but we don't know. And by no means I can propagate giving a GLP-1 to a 1-year-old. These are very complicated questions for obvious reasons, right? The biggest question is when you come to GLP-1s in type 1, whether there is an effect, what you would call flogging a beta cell that's already under attack, and whether you do something detrimental. And I think that's one mechanistic aspect that needs to be clearly sorted, and we are working on that. We would think if that had been the case, the patients in our trial would have failed all while they were on therapy at different times. Like you flog the beta cell, poof, it goes down, no matter whether you treat. But we didn't see this. We saw an effect and then this parallel decline that you see in many trials, and then we stopped treatment and then it went down. That's different, right? The stopping treatment doesn't worry me so much in the sense like if you take an antihypertensive, or actually with statins, it's very clear. Your cholesterol is high, you take the statin, it goes down. But you stop taking the stuff, it goes up high again. So it's like a normal thing that you would see clinically, right?
So one little technical question. So the image you showed, the video you showed where T cells attacking organoid, islet or pancreatic.
Yes.
Organoid. Is it an allo or it has to be an allo, right? Allo.
Yes, it's allo. And if we want auto, we have to spike in the clones. That's how that goes. Yes, it's essentially an MLR. But we figured we start with this because it's easy to do. We have all the players there, except for some macrophages by nature of isolation. And then we can subtractively work from that and spike things in. Doing this with the same donor from type 1 and growing out autoreactive lines, I think will be possible. And we do want to do this together with Sally Kent, but it's much more involved at the first stage. So it's an allo MLR with spiked in clones. We think now that you can say is relevant for islet transplantation, for obvious reasons, but that's what it is.
Very good.
I think I'm afraid I need to run. I have 1 minute to log into this other thing to induce my postdoc. But if you have any other burning questions, just send me an email to Matthias at lgi.org, and very happy to continue the conversations.
Yeah, no, thank you so much, Matthias. And hopefully, we would be able to invite you sometime in person for our seminar in the future.
Yes.
And thank you so much for doing this, and have a great weekend.
Yeah,
Yes,
thank you again. That was outstanding talk. Thank you so much.
Thank you very much. And it was a pleasure to seeing you all, albeit over Zoom, but it's not so bad. You can actually...
We invite you in Charleston. It's actually interesting city. Yeah.
Yes, I have been there before. I would love to.
Yeah. Thank you. Thank you again. Bye.
Bye.